H is low dimensional hidden, B is high dimensional, so F will be some thin matrix, C is some constant, and epsilon is going to be Gaussian noise, which is distributed in the following way with zero mean, and it's going to have diagonal covariance matrix. And there are two cases. One is a full general diagonal matrix, no restriction, and the other one is that it's isotropic, so that the entries of the diagonal are all the same. Okay, and it's got a special name, probabilistic Pca. But factor analysis is this one, and probabilistic Pca is just a very special case, or a special case of factor analysis. Okay, so this is the most important thing to consider. So, the probability distribution, we can write this down as a latent variable model, P of V given H. So it's a continuous latent variable model. It's a Gaussian distribution V with a mean given by FH plus C, and the covariance given by psi. Okay, we've got this Gaussian prior over the H's, and we may sort of assume actually that this Gaussian prior has got zero mean and unit covariance. Okay, so if we were then to say what is the corresponding then probability distribution for the data, P of V, we'll get that by just integrating P of V given H times by P of H over H. And that is going to give us a Gaussian distribution in V, with mean given by C, and covariance matrix given by FF transpose plus psi. Now, how did I get this formula? One way I could do this, I could say, well, I know what P of V given H is, this thing, e to the minus blah blah blah, over the determinant of, psi to the power half of 2 pi here and there. I could write down P of H in here, and I've got some H dimensional integral then to compute, and I could work it out, right? I didn't do that. I just wrote the answer down straight away in my head. And you ought to be able to do this as well. Okay. So how do I know it's that? So this is important. So it's a very, very useful trick. Okay, so let's say so I know that epsilon is Gaussian distributed, and I know that H is Gaussian distributed. So we could do this thing, we could write down, we could do this, exercise where we write down what is P of V. It's the integral of e to the minus H plus C transpose psi, this is phi inverse FH plus C over 2 pi psi inverse, right? Times by e to the H transpose H over 2 2 pi to the H over 2. dH. And we could go through this, nice exercise now, saying, well, okay, whatever it is at the numerator, I have to integrate over. Sorry, I missed the V on here. E minus. we could say, we could recognize that the exponent here is a quadratic in H. And then we could collect the terms, the quadratic terms and the linear terms. We could complete the square, recognize this looks like a Gaussian, compute the Gaussian integral, go through that, get a messy expression. You realize using the Woodbury identities, matrix inversion lemma, that you can simplify the whole thing. It's fine to do that. That's a good exercise to go through. You do that once in your lifetime, and you never do it again. Okay? Because there's a trick.
Okay.
Hello? Don't recognize you.
The same thoughts or not?
It's not this, no.
Cool. Yeah.
Okay, so the thing to recognize is that when you've done that completing the square and you integrate it, think about what happens. The only thing that we'll end up with is you get this kind of residual term, which is like the thing you have to add on. But whatever it will be, an exponent will be a quadratic function of v after you've done the integral. Right? The only thing that this thing will be some, after doing the integral, we'd have some e to the minus quadratic function of v. Some linear terms or quadratic terms. Okay. That tells you, well, if p of v is proportional to e to the minus some quadratic function of v, well, it must be a Gaussian in v. Right? That's what it means, basically. So, if it's a Gaussian in v, that means you only need to find this mean and its covariance. And then you're done, right? You just say, well, that's it. So here's an algebraic trick, which I'm not going to prove to you is correct, but it's intuitive, and you can prove it's correct just by following it formally and again doing completion of the squares. But the following thing works. I want to find the mean first of v. Okay, so I'm going to do this thing. So this is a kind of characteristic linear algebra trick. So what is the mean of v? Well, v is given by this expression here. So this only works, by the way, because everything is linear operators. But is any linear, because it's a linear operator, it works. So what do I mean by expectations? I mean, just think about it in some general sense. So c is a constant. Okay, this is taking the expectation of this equation. What's the expectation of h? Well, h has got mean 0. So that's 0. What's the expectation of epsilon? It's got mean 0. So that's 0. So the mean of v is 0. Oh, sorry, c. Okay, so we need to find the covariance matrix as well. Now the covariance matrix is given by, in general, v transposed minus v transpose. That's the covariance matrix. Okay, but we just said that the mean of v is 0. So c. Sorry. Right, okay, so this is cc transpose. Okay, so we need to find what is the expectation of v transposed. So we can do that. We can write down v plus fh plus c plus epsilon plus v plus fh plus c plus epsilon transposed. We take the expectation of this thing. Okay, so this looks painful, but it's very easy. What we're going to do is think about multiplying out all these terms and then averaging them. Okay, so for example, we're going to have a v transpose term.
Yes.
That makes more sense. this term here, sorry, f h. So the transpose of this is h transposed f transposed. Okay, and then we take the expectation of that. That would be the first term. The second term would be something like fh c transposed, expectation of that. But the only thing that's changing there, well, maybe I'll write it on there actually, just to. So fh c transpose, expectation. Right, and the third one would be plus expectation of f h epsilon transposed. And then there's a kind of like the symmetric part of these two. Then there's like a C transposed. There's going to be some other terms. I'm not going to write all the symmetric terms there actually. This the average of C epsilon transposed, plus the average of epsilon transposed, plus a couple of more which are just a symmetric part of these ones. Okay, so this one here, C and F are constants, so this is the expectation of H here, which is 0. So this goes to 0. C epsilon, C is constant, epsilon has got means 0, so that goes to 0. H and epsilon are independent a priori. Okay, so this is the average of H times by the average of epsilon, but they're both 0 mean. So this is actually 0 as well. And epsilon transpose. Well, epsilon has got mean 0. So epsilon transpose is the covariance of epsilon, which is given by psi. So this is just psi. Now let's look at this term here. F is a constant, so we can bring this expectation in here. H has got mean 0. This is the covariance of H, which is the identity. So we're just left with F transposed plus psi plus C transposed. But we're going to minus C transpose at the end, so we'll subtract it off. So this is the covariance matrix. Okay. So, this looks complicated, but of course, actually, when you see this, you know all of these terms are cancelling. The only things which are not going to cancel are this term here, so F times by the covariance of H, F transposed. The only other thing which doesn't cancel is epsilon transpose, its identity. That's psi. So you know instantly, actually, you don't need to go through this step at all. It's just instantaneous. You can literally do it in your head. Okay, so if you like, you can try to write down, justify this mathematically, but it's correct. So this is a big, you can use a similar kind of trick sometimes for other situations, where you want to find, like a conjugacy thing, like I know the distribution has to be of this form, this resulting integral, so therefore I only need to find the moments of it, and then you don't have to worry about anything else. Okay, yeah?
For the FH epsilon, you assume that H and epsilon are independent?
Yes, yeah.
Okay. Condition of the model?
Yeah, it's a condition of the model, yeah. So the one way to think about this is that we have this H term here, so we have these, in terms of the graphical model, we've got these V's, V, whatever dimension is. Yeah, so one way, I didn't write this down, we're putting noise on these V's, but another way to think about this is that actually you can write it this way. So what this means is that this is a deterministic function now. It says v is equal to h plus f times by h plus epsilon, and the epsilon is itself distributed independently with noise. So you see here that these are a priori independent variables, basically. So okay, so that's the so you, like I said, you can do this if you want. You write that down. And after some algebraic manipulation, using the various Woodbury or matrix inversion lemma, you'll get this result. It's in a much more painful way. Good. All right. So the other thing to say is that I claim that you might think at the moment. So we've got this. This is the factor analysis graphical model, and we've got an independent assumption on these latent factors h. But actually, so you might think, well, that's great. I'll write a new paper and I'll use a more powerful model, which I consider correlated h. I'll extend the model. That's a new paper. Actually, that has brings nothing. And the reason is that let's think about this thing. Okay, so the only thing that h does is, if we were to go back to this expression down over here, right? That would have been everything would have gone through as before, except now we would have put here the covariance of the prior on h. You could call that, say, C or something like that. So in the general case, if P of h is distributed with a normal distribution, say zero mean, and covariance, say C, we just end up with a covariance for V to be F C F transposed plus a sign. That would be the resulting covariance, right? But C is a covariance matrix, so it's got a square root, right? So we could define some matrix, say C to the half, and it's symmetric as well. Doesn't too much, but you could say that's equal to F C to the half F transposed. Right. Well, I could say C is symmetric, so I could say this is the same as, I call this F tilde as F tilde transpose, where F tilde is equal to F times by C to the half. And it's the same, right? So the covariance matrix, so then, the whole covariance matrix of V would be of the form F tilde transpose plus psi. So F is a free parameter. We're trying to learn F. There's no constraint on F. It's just a matrix we're trying to learn. So similarly, there's no constraint on F tilde. So you may as well call F tilde F. There's no difference. So it doesn't bring you anything. This correlation doesn't help. But this is just a property. I'm not saying this is a general property of graphical models. It's just a very special property of this linear Gaussian model. It doesn't generally hold, but in this case, you don't gain anything by including dependencies in the latent variables. Okay. Yeah.
The FF transpose, is that the projection?
Well, F itself is the up projection matrix. It's like the it's a bit like the basis measure. The columns of F would form like the base vectors, if you like. And H is corresponding to what we called Y before. That's like the latent coordinates, basically. Okay. So that's a typical exam question, by the way. Why should you don't need to bother with this correlated prior. Okay, so these things are called pancakes or saucers sometimes. So the picture is the following one, that let's try to, a good way to think about distributions is to generate samples of data from that distribution. So how does this work? Well, we've got P of H and then P of V given H. So we could draw a vector H from a Gaussian distribution, zero mean, unique covariance, okay, for H. Given H, and given an F, we can compute F times by H, and then we add on some Gaussian noise from epsilon, which is basically zero mean and got some covariance, diagonal covariance psi. So these are the points drawn F times by H before adding on noise. So these correspond to like a Gaussian distribution in the plane. Okay, and these are not necessarily. This could be elongated because the F is not necessarily orthogonal. No, the columns are not necessarily orthogonal. And then what we do is we add on some noise vector, which is in this case a three-dimensional vector. So these are the corresponding then. So that point might get then given to added on to this point. So this will take this noise will take us out of the plane. And so if we were to generate many data points, we would end up with a kind of a Gaussian, the highest probability will be here in the center, and less likely at these points here. And then we'll basically end up with a sort of widening this sort of in-plane vector, or in-plane saucer, to give us a kind of a plate, basically, like a galaxy, if you like, around this thing, with a concentration at the center of this plane. But what that means is that this model will be good for data that's distributed like that, with some central point in a plane, and there's a small amounts off the plane. So of course this is looking very similar to PCA, but this is a probabilistic model. Okay, so maybe I won't go through all the details here, but maximum likelihood, we just want to learn now three things. We want to learn C, it's constant, we want to learn matrix F, and we want to learn this diagonal matrix psi. Those are three things. We want to do that with maximum likelihood, and we'll assume, as usual, that the data is IID. So we just write down the objective function to maximize, it's this. So this is in terms of the log likelihood, this is what you get. So that's it, where this sigma d is given by this covariance matrix. So that's your mathematical task now, to figure out what the solution is of this thing. And it turns out that there is no closed form solution. But what you can do is, at least for C, if you differentiate this, that's easy. It's just a quadratic form in C. So immediately you get that C is given by this, which is just the mean of the data. That's good, that makes sense, right? So this constant is just the mean of the data. You can then plug that back, the C setting, which is the mean of the data, into there. And then we could just switch around, this sum. So this V minus this mean transpose sigma. We could write that, that's like x transpose y is the same as the trace of xy transposed. Alright, that's handy to do that, because we can then basically re-express this in terms of the empirical covariance matrix. So this is another classical algebraic manipulation that's useful. So this term here is, let's say, of something of the form V transpose, say, some matrix M times by V, where V is maybe subtracted with something. But this is equal to the trace of V transposed. Okay. This is useful because when I've got this sum now over n here, if I were to write in this form, I don't know how to bring this sum together. I cannot collect, have an interaction between these two v's. But this way, my sum over n, because this is all linear, I can bring this sum over n now inside this linear operation here. Sum over n, and this object now is just some simple object. It's just essentially the covariance matrix of the data, the empirical covariance. So that's the why it's very useful to know this algebraic trick. Without that, it's very complicated to do this problem. So that's what I'm doing here. So I write that inner product as a trace of an outer product term. I can then bring the sum over the data points inside to get basically that's a trace of sigma d inverse times by the empirical covariance matrix, just scaled with the number of data points.
Why would you want to project your data to a high, in terms of practical applications? Why?
Well, it's kind of it's the opposite way around to PCA. In PCA, you have the data points which are high dimensional, and you project down, if you like, to a low dimension. But the other, the converse way of viewing that is to say, well, actually, I have this latent low dimensional description, and I want to to project up or to get a kind of higher dimensional picture.
Are you assuming that the low dimensional projection is not the optimal? Is that what you're assuming, that you basically had some high dimensional data, you project it to a low dimension, you can then like reconstruct to a high dimension, then do the optimal? Is that kind of what?
No, it's like the idea is simply that when you think about this sort of graphical model, generative modeling viewpoint, you think about some. So your idea might be, although I have this very high dimensional complex looking object V, I believe there exists a low dimensional representation or a way to generate this data which is much lower than V dimensionality. And so you then write down what you think that model is. In this case, it's this one. So I start out with this low dimensional H, which gets projected to this higher dimension Y, or sorry, V.
We're observing V, right?
Yeah.
So we're interested in H.
Yes.
Same idea as PCA, right?
That's right. Yeah. So what we will do is we'll be interested in finding out what this projection or this matrix F is. It's not a projection matrix, it's the opposite, it's going up now rather than projecting down. It's like the basis matrix basically. And then we'll be interested also in finding out what is P of H given V once we've learned the parameters, because we'll figure out what is the distribution of latent coordinates given this high dimensional V. You'll see hopefully in a minute, but maybe it gets clearer. Okay, so now you've only got two things left now. You've got the psi and you've got the f, right? You've got rid of c. You have to now maximize this expression with respect to psi and with respect to f. Okay, so the problem is that's not doable, and there's no closed form solution for that. But one thing you can do is you can fix psi and then optimize with respect to f, and you can then do the opposite. You can say fix f and maximize with respect to psi. So it's again a similar coordinate-wise approach, right? And both of those stages there exist closed form solutions for them. So it's not so bad, right? We just iterate them, those two steps. And maybe I won't go through the derivation here, but it's an interesting algebraic exercise actually. So we need to what's called symmetrize a problem. That can be done through this new sort of symmetrized, kind of symmetrized covariance matrix S. It's kind of like a rescale thing. So basically, everything becomes isotropic within this scaling, something like that. Or not isotropic, but it becomes effectively rescale. And then you can read the details in the notes about how to do this. And you'll find out that the optimum solution then is to take this sort of rescaled covariance matrix, sampled empirical covariance matrix, compute an eigendecomposition of it, and the F is given by essentially the rescaled diagonal rescaling of the leading eigenvectors of this decomposition of your covariance matrix. Just rescale again, post with another diagonal matrix here. And R is an arbitrary rotation matrix. So this corresponds to the fact that, as you saw, because we've got FF transpose, you can rotate F any way you like. So it's a similar kind of problem before. There's an invariance there, and that invariance is expressed through this arbitrary orthogonal matrix here. Okay, so this is the optimal solution for f given psi. And then you can more easily show that the optimal psi for given f is just given by this expression here. So it's just given by the diagonal of s minus ff transposed. So this is easy. So you basically you make some guess of, say, psi. Maybe you set it the identity matrix to start with. Given psi, then you just make an update here. So psi to start with would have been the identity. You take, u is just the decomposition of this matrix here. Okay, you go through that. This gives you f. Given f, you then update psi with this. Given that psi, you go back, update f. Converges rapidly, this procedure. Just after a few iterations, you'll have the optimal f and optimal psi. And this procedure is I think the classical one which you'll find in most numerical packages for learning factor analysis. And it's a very old procedure. It goes back to the 1960s, even earlier. So more recently, people thought about probabilistic Pca, which is a special case. Although, to be honest, I think they didn't really know enough about the literature about these guys. But anyway, it's effectively really just a trivial exercise in some sense, because all that you need to do, you already know what the optimal solution for f is. It's just given by the expression. So all you need to do is just to plug in, given this psi, what is the optimal formula for psi under this diagonal constraint. And it turns out there that actually you can show that the whole thing sort of simplifies a little bit, and you just reduce to basically Pca. So this is used now. These are the eigenvectors of the original covariance matrix, not the rescaled version. And you just need to take the leading eigenvectors of the sample covariance matrix. And you have a slight difference from classical Pca because you have this just the f is to kind of like rescaled slightly by this diagonal matrix here. So formally, Pca is a limiting case of this probabilistic Pca when sigma goes to 0. So when your assumption about the noise off the plane is that it gets very small, then it starts to get exactly close to exactly matching the Pca solution. So the details are given in the notes, but okay, so what's the difference between these things? So here's some digits, some handwritten sevens, and
It's an experiment.
Okay, so I've taken a bunch of sevens and I tried to fit factor analysis to them using some dimension which I didn't write down, some low dimension, probably 10 or something like that, I would imagine. Okay, so these are these images are whatever 700 dimensional vectors, each of them, and I've got a collection of them, a few hundred of them, and I try to fit this, say, 10-dimensional H factor analysis. And then what I can do is I can, once I've learned that model, I can try to do a reconstruction of data. So when I've learned psi, and when I've learned f, and I've learned c, I can generate some data from this factor analysis model. As before, right? I generate a H from a Gaussian distribution with zero mean unique covariance. I multiply that with f, and then I add on some Gaussian noise from the epsilon process, and that will generate an image. That gives me a v vector, which I can then plot as an image. And these are samples. These are 25 samples from the learned factor analysis model. Okay, so you can't see this very well, unfortunately. Try it again. No, it doesn't want to know at all now. There's something weird going on with that. Okay, so the thing to notice is that on the extremities of this image here, even though they rescale, unfortunately, with colouring, but these are basically all zero, these elements here. The image, the model is not generating any, it's always generating zero towards its edges, which is right? That's the correct thing to do. We don't have any thing going on in the training data in these extremities here. On the other hand, the PPCA, these are samples from the PPCA model. Remember now that every component of the vector the vector v has got the same variance of the noise, sigma squared. Right? So that means when you generate now, every single pixel here has got the same covariance, the same variance as each other. So there's no way that you can get these sort of regions where at some points the variance is low and at some points the variance is higher. It's not possible because it's always got this constant additive variance term. So this, in a sense, is less useful, maybe you could think, because you don't have this sort of spatial flexibility that you do have in the factor analysis model. So that's the distinction, if you like, between PPCA and factor analysis. So factor analysis is, this is a very classical statistical model which goes back probably since the 1940s, maybe even earlier. And a lot of people use this model to try to understand relationships in data, and a lot of psychologists use this kind of information as well. So yeah, and this PPCA it's nice. It's a simpler model. It's nice in the sense that it's a probabilistic description or close to of PCA. So you can do all the kinds of, if you like probabilities, you can do all the kind of things you might like to do, like making mixtures of these things. Of course, you can make mixtures of factor analysis, etc. So it's not clear to me sometimes, to be honest, why one would need to use PPCA. It's a little bit. You may as well just do factor analysis because it's just as easy and it's a more powerful thing. Okay, and the final thing is that you may come across something called canonical correlation analysis, and so to my mind this is just factor analysis. So what is the idea here? You might have, say, two sources. Let's say this is the video, just the images of the video. This might be an image, and this might be a corresponding, say, audio for that image, or maybe there's a few frames of a video. This might be the corresponding audio signal for that video, right? So you might think, well, there's something which is going to correlate these two streams of information. Something like, for example, I would expect that the mouth should be correlated with the sound, right? There's something low dimensional which is going to perhaps explain the correlation between the video and the audio, and that a very simple model would be to say that's a linear effect, that there's some H which is latent and common to both these things, which is generating in some way both of these things, right? So you could have this kind of structure. Again, it's a conditional independent structure. This H is making X and Y conditionally independent, and run through the whole thing. If these are linear and Gaussian, so if this X is a linear function of H, and similarly if this Y is a linear function of H, okay, this is a scalar case for H, then you can show that all this is just factor analysis, in which the matrix F has got some block structure. And you can then generalize this to having a vector H here. Again, it's just a block structured F matrix. So really, canonical correlation analysis, to my mind, is just a constrained factor analysis model. But you'll see people, discussing it in other ways, which, so I'm less in agreement with their perspectives, but this is my perspective. So I think it's what I'm trying to say is it's very important to understand and to be aware of factor analysis models. So many people in the machine learning community, I've seen so many papers talk about canonical correlation analysis, and they don't even realize it's just factor analysis. Okay, from the statistics community, just a special case thereof. Okay, so it's important to bear that in mind. Okay, that's it. So, like I said, remember, I hope to see you in 2 weeks' time. Check your emails just in case I get delayed.